Things you should say. You good?
Sorry, you can keep talking. I didn't realize I changed it. Not good. We have another minute. I know. So, I can't start early. All right. Hello, everybody. Can you hear me? The clock is now 12:15, so we are going to start. Okay. Can you hear me with the mask on? Yes. Super. Okay. It is my distinct pleasure today to introduce Wren Suess. It is a pleasure for three reasons. The first is because of her incredible scientific impact. Not only did Wren write one of the first 10 papers to come out of the James Webb Space Telescope, one of the first 10. That happened in 7 days, I believe? 7 days within of the first data dropping. But she also upended our understanding of galaxy formation with some of the work she did. In particular, this work, when this paper first came out, she's going to tell you about it today. When this paper first came out, every meeting I was in with a collaborator for the next 3 months was like, this Suess paper cannot possibly be right. Because it had such a huge impact, it changed how we thought galaxies grew. It turns out there's been a number of follow-up papers on this topic now, and it has been shown to be right. We still don't understand how it could possibly be right, but it is. So Wren will talk about that as well as a number of her other incredible findings today. The second reason I'm excited to introduce Wren today is because of the way she has made astronomy more inclusive. She developed a program which is now implemented in 10 different departments that talks about how to make respect part of research. She'll talk briefly about that, I think, as well. And finally, she is a product of CU Boulder undergraduate education. So, woo! And you'll see why that should make us all so proud during this talk. So everyone, please join me in welcoming Wren Suess.
Excellent. All right, thank you. Is my mic on? Good? Okay. Thank you so much for the wonderful introduction, Erica. So it's really exciting to be on this side of the auditorium. I was an undergrad at CU years ago, and went to many colloquia and understood maybe half of them. So hopefully I do a little bit better during this talk. So I'm really excited to tell you about a lot of recent results from the James Webb Space Telescope and also ALMA, which is the Atacama Large Millimeter Submillimeter Array. This is a really, really exciting time to be studying galaxies. We've only had data, like Erica was saying, since about mid-July, so it's very early days, but the results that we're getting from this incredible new telescope so far are already really transforming our understanding of how galaxies form and grow over time. And this is work that's been done with a lot of wonderful collaborators, including Erica. I'm a joint fellow at Stanford and Santa Cruz. So I want to start by just showing you this, this photographic plate of Andromeda, which is our nearest local neighbor galaxy, taken in the 1920s. So astronomers have been studying galaxies for many, many decades at this point. And there's a couple reasons that we really care about galaxies, and hopefully I can convince all of you to care about galaxies as well. The first is that galaxies are tracers of cosmology. So galaxies live at the centers of dark matter halos. And so you can look at where galaxies live, how massive they are, how they're clustered on the sky, and start to learn about the actual kind of fundamental cosmology that's governing our universe. But also, I think galaxies are extremely interesting in their own right, and that's because the integrated properties that we observe from galaxies reflects this really complex interplay between all of these different components that together make up the galaxy. So we're seeing the light from stars. We're also seeing this multi-phase gas, everything from very cold gas to very, very hot gas. Dark matter, most galaxies host supermassive black holes. And all of these components are kind of interacting with each other, and there's no way that we can model all of this simultaneously because it's just too complicated. The length scales are everything from atoms to the entire observable universe, and the time scales, again, are kind of, the atomic processes happening on very short time scales, 2 billions of years. And so studying galaxies is this kind of complex, messy problem where what we're trying to do is really understand the physics that's important at that specific moment in time governing the galaxy's evolution. And so this is obviously a quite old picture of a local galaxy. We've done much better in the intervening decades. These are some images from the Hubble Space Telescope of galaxies in our local neighborhood. So these are both spiral galaxies. Galaxies tend to broadly be classified either as these kind of star-forming disks like we see here. This one has a nice bar on it. And then also these galaxies that are no longer actively forming stars that tend to be kind of elliptical, much redder. They often can be found at the centers of these massive galaxy clusters. And so these are kind of the fossils of galaxy evolution that we see around us today, the products of 13 billion years of evolution. And so what you can do is to look at these local galaxies in detail and try and kind of decide what processes made them look the way that they look now. But as astronomers, we also have a time machine, right? Because we can look far away, and that's the same thing as looking back in time because of the finite speed of light. And so we actually don't just have to look at things in the local universe. We can actually look at the distant universe and directly observe the kind of progenitors of these galaxies as they're in the process of forming, which is really awesome. But also, we didn't think for a long time that we would actually be able to do this. Because with ground-based telescopes up through the 70s and the 80s, we simply couldn't see distant galaxies above the noise and the pesky atmosphere that's between us and the sky. And so we thought, basically, that when we launched the Hubble Space Telescope, that if galaxies in the distant universe looked like these galaxies we see today, we also thought we wouldn't be able to see them with Hubble, because they just would have been too large, and they would have been too low of surface brightness. So even if we integrated for a really long time with Hubble, we probably thought we wouldn't be able to see these galaxies. And so everything really changed when we actually did launch Hubble. And we decided to continue in what I think is a wonderful astronomical tradition. So at the launch of one of the telescopes at the Palomar Observatory, they asked Edwin Hubble, after whom this telescope is named, what he really hoped to find with this new instrumentation. And what Hubble said is, we hope to find something we hadn't expected. And I think as astronomers, it's really important that we continue to do this process of looking for things that we hadn't expected, looking for things that disprove potentially our models, and trying to add those into our understanding of the universe. And so when we launched the Hubble Space Telescope, the community decided to spend 10 full days, which is just like an egregious amount of time, staring at a basically blank patch of sky, despite the fact that we thought that there wouldn't really be anything in it. And what we found, of course, this is a familiar story, is not a blank patch of sky. It was the first ultra-deep field. So this is the Good South ultra-deep field. There's a couple of stars in here, 1, 2, I think another one. But everything else in this image is a distant galaxy. And most of these are when the universe was half or less of its current age. And so the reason that we could see these, fundamentally, because we didn't think we could, is that these distant galaxies don't look like their local counterparts. They're very small, they're very clumpy, they have much higher surface brightnesses, and so we were able to see them after all with Hubble. And so I wanted to kind of come back to this story of this first ultra-deep field because I think it's a really good example of just how transformative new instrumentation, especially new space-based instrumentation, can be. And so the same way that this was a watershed moment for extragalactic astronomy, we're at the very beginning of the next one of those moments because we just launched this new James Webb Space Telescope. And just as kind of an example of that, overnight when we took this picture, the number of galaxies that we thought existed in the observable universe increased by a factor of 5. So it really is a dramatic change in our understanding of the universe. And so as soon as we kind of knew that galaxies must change between the distant universe and today, the question became, how does that change happen? So the universe at high redshifts here, galaxies tend to be relatively small, they tend to be clumpy, they have these very bursty star formation histories, there's a lot of cold gas floating around in the universe. And then in the local universe, things are relatively large and massive and gas poor. And so the question is just how do we get from there to here? And there's a couple of really big unsolved questions that I want to kind of focus on for the purposes of this talk. The first one is when and how did the first galaxies form? This is one of the many things that JWST was really built to do, so I'll tell you about a couple of the first results on that. Also, how do galaxies grow over time? How do their sizes change? And what are the kind of physical processes by which they're assembling their stellar mass? And then why and how do galaxies stop forming stars? Why do we see this bimodality between these disky blue star-forming galaxies and these quiescent red elliptical galaxies? And the reason that we kind of still have these open questions, I would argue, is that we've been fundamentally limited in our wavelength coverage of the distant universe. And there's a couple of ways in which we've been a little bit limited. The first is that, back in the kind of original days of astronomy when instrumentation was extremely hard, everybody worked in their one very specific wavelength regime and didn't really know how to talk to other astronomers that were using different techniques. I see some laughter. So I think, to a large extent, that's improved. But there's still a big gap between optical, ultraviolet, near-infrared astronomers and sub-millimeter far-infrared people. And that's really because both the instrumentation is different, and it is actually pretty hard to do some of these observations, but it's fundamentally because the sample of galaxies you're looking at is different. Things that are bright in the sub-millimeter are not the same things that are bright in the optical, and so you end up with a kind of semi-overlapping but mostly disjoint view of the galaxy population. And you end up with things like, for example, there's recently been, in kind of the past 5 years, this big kind of surge of papers on these HST dark galaxies, which are kind of, but not entirely like sub-millimeter galaxies, which there's been literature on for many decades. They're kind of the tip of the iceberg, and it's hard to see how the populations connect. And so I'll argue later, once I'm talking about JWST results, that this is kind of the first time that we'll be able to actually kind of unite these two communities and move forward with a complete picture of the galaxy population across cosmic time. The second reason that it's been difficult to answer these big unsolved questions is that to date, we haven't had any high-resolution rest frame infrared imaging. And so basically Spitzer is the best that we've had, and it's just, it can't resolve distant galaxies because it's really hard to put a really big mirror in space, and it's hard to observe the infrared from the ground because there's all this water in the atmosphere that absorbs in the infrared. And so there's two reasons that we want this rest frame infrared imaging. The first is that Hubble can't see the formation of the first galaxies. So looking back in time, we can just look at galaxies that are far away, but we also, because of the effect of cosmological redshift, the further and further away we look and the further and further back in time we want to look, the further into the red we have to observe. And so basically Hubble is here. The reddest band on Hubble is at 1.6 microns. And so it can see the light that's emitted from local galaxies and also kind of, it stops just short of the first galaxies, effectively. And so in order to see these very first galaxies forming, you have to look further into the red part of the spectrum, which is exactly what JWST was designed to do. And then the other reason that you want to observe galaxies in the infrared is that even if you're not just trying to look at galaxies in the very local universe, you want to see the light that was actually emitted in the infrared. And that's because of the effects of cosmic dust. So dust basically is some sort of screen that is between us, and it absorbs photons that are emitted, and you can't see the full distribution of light that's coming from your galaxy. So this is an example of this is a local galaxy. This is a face-on spiral galaxy as viewed in the ultraviolet, where you can see basically there's just a couple bright clumps in this galaxy. Everything else is obscured by dust. These are kind of the brightest star-forming regions that you're picking out in the rest frame ultraviolet. If you go to the optical part of the spectrum, all of a sudden the galaxy looks quite different. You can start to see the center of this pop out, and then you can see these beautiful dust lanes out in the spiral arms. And then if you go to longer wavelengths in the infrared, all of a sudden you can see that this galaxy is a disk. You can see this kind of Keplerian disk profile of the thing that was completely obscured at shorter wavelengths. And so basically when we're trying to look at galaxies, even at kind of redshift 1 to 2, where we would like to observe this full multi-wavelength picture, with Hubble we've only been getting this light. We've been missing the rest frame infrared that's truly tracing the mass distribution of the galaxy. And so these kind of two reasons, seeing the first galaxies and seeing these actual mass profiles, are some of the things that led us to basically build the single most expensive, complicated observatory that humans have ever built. So this is the James Webb Space Telescope. It features 18 different mirror segments. They're gold-plated beryllium. They're all these little hexagons, so you can position them and get a perfect mirror once the thing is in space. Also, we're trying to make faint measurements of infrared light, which of course is heat. So you have to put it very far away and shield it from the sun and the earth and the moon, so it's able to actually make sensitive measurements. So it's got a tennis court-sized sun shield between it and the sun. And then, of course, you can't launch an entire tennis court into space. So it also has 139 actuators and 8 motors that all had to deploy exactly perfectly to unfold it once it's way far away in space where we can't touch it. Right? And as if this wasn't hard enough, it's also orbiting 1 million miles away, which is basically the furthest we've put anything other than things that we send to other planets. So this is much more difficult than Hubble, and this is ultimately why this project took so long and why it took so many engineers working for so many years in order to make sure this thing would work perfectly. And spoiler alert, it did. So the launch, I'm sure many of you watched it, was last December, and this is actually the last view directly that we'll ever have of JWST as it's kind of drifting off into space here. This is from the Arianespace Stage 2 rocket. And so the launch actually went incredibly, incredibly well. The mission was supposed to be limited by its fuel, and basically the launch parameters were so perfectly on spec that it added another estimated 10 years to the total mission lifetime, which is extremely cool because we were all worried about trying to do all our science in 5 years, and now we get like 20. Hopefully, if nothing else breaks. I shouldn't have said that. So after this process of launch, there was about 6 months of the telescope unfolding. Again, everything went perfectly. And it getting into orbit at the second Lagrange point, and then this commissioning process of ensuring that all the instruments were well calibrated. And so to show you just how dramatic of an improvement we're getting in this infrared part of the spectrum, this is a image from Spitzer, which again, amazing telescope, the best we'd had up to this point, of a couple stars, and then maybe something here. And then this is going to fade to the JWST, one of the commissioning images, where you see all of a sudden those giant fuzzy blobs of stars go down into these tiny point sources. They're diffraction limited, so you can see the telescope diffraction pattern there. All of this emission is all of a sudden you can see it detected very clearly. There's all these sources that weren't in Spitzer at all that suddenly we're finally able to beat down this noise and see. Some of the Spitzer sources are resolved into multiple different components. I mean, this is just like the coolest, right? And so as soon as this data started coming out, I think everybody I know was just waiting with bated breath for the first public data release so we could start to actually get our hands on this entirely new view of the universe that we can get from this new telescope. So with that, I want to kind of return to these big open questions and start to ask, what have we learned in, again, we've had data since July, so this is a lot of this is still in flux, and I'll talk about some older stuff as well, but what have we already started to learn from this new telescope? So I'm going to start with when and how the first galaxies formed. So there's been a lot of work on the very, very first galaxies that are potentially reionizing the universe. Some of it I was involved in. I'm not going to actually talk about it because I have too much to talk about today. And also, I think a lot of those results are kind of awaiting confirmation from spectroscopy, which will happen very soon. What I do want to talk about is the very first massive galaxies. And so this is a paper led by my collaborator Ivo Labe, where we decided to look for galaxies where we see both the Balmer and the Lyman breaks. So normally when you're looking for very high redshift galaxies, you're just looking for one break in the spectrum, the Lyman break, because blueward of that, all of the photons are absorbed by the IGM. And so there's a fundamental kind of degeneracy where you don't actually quite know what the redshift is because you're really hoping it's a Lyman break and not a Balmer break that you're seeing from a lower redshift galaxy. So what we decided to do was to look for galaxies where we see both of these two breaks in the spectrum, the Lyman break and the Balmer break, because that gives us really secure estimates of the photometric redshift between this kind of 6 to 10 range here. And so what we found actually were 6 extremely massive galaxies at these high redshifts, much more massive than we were expecting. So this is the stacked spectrum of these things. So the red is the galaxies that we found in JWST from Ivo's paper. And then the green is a stacked spectrum of all of the galaxies that we previously knew of at these high redshifts with Hubble and with Spitzer. And you can see that these curves look entirely different, right? So these red galaxies that we're seeing for the very first time are so much redder. They have a totally different spectral shape than the types of galaxies we were seeing previously. And this is just a selection bias, right? These things were too red for us to have seen them before. And these red colors are implying extremely high masses, probably, we think. I'll get to that. But this is the cumulative stellar mass density as a function of stellar mass. So basically, how many galaxies of a given mass do you have? And these are the curves expected from previous observations at both redshift 8 and redshift 9 from HST and IRAC. And if you put just those 6 galaxies that we found in the very first imaging that we got from JWST, you get these curves, which are more than an order of magnitude higher stellar mass density than was previously expected from Hubble and IRAC. And so this was really surprising to us. We were expecting to maybe find one relatively massive thing, and instead we found 6 things that are extremely massive. And so when we put this paper out there, we were just really excited about how different these galaxies were than previous populations we had seen. But kind of immediately, there was a pretty big splash because people started worrying that these galaxies are actually so massive that they might break the universe. Right? So basically, to walk you through this, if you have a given model of cosmology that predicts the number of dark matter halos that you have and the amount of mass that's in those dark matter halos, and that's just from your cosmological model. And so then if you assume some baryon fraction, so how many baryons do you have for the amount of dark matter, and then how do those baryons get turned into stars, so how many stars are you allowed to form out of your baryons, basically you can get from cosmology alone an upper limit on how much stellar mass is in the universe at any given time. And so Mike Boylan-Colchin led this, actually he was a single author on this paper, which is basically these are showing Again, this is a mass function, so this is the mass density as a function of stellar mass. And these curves are assuming different efficiencies for turning baryons into stars. And basically, these are the limits from cosmology, and these are the points from Ivo's paper. So basically, they lie, these have come down a tiny bit with some additional modeling, but they lie right on this curve of being basically all of the baryons in the universe are in these galaxies at this time, which is a little bit crazy. So, I think it's a little bit of early days to say that we broke our cosmological model. I think we have many tests of lambda CDM that are a little bit less wobbly than what are the masses of distant galaxies. But basically, I don't think we broke the universe, but I think something really interesting is going on here and something really unexpected is going on, right? Because we did this modeling to get the masses of these galaxies the same way that everybody else in the community does the modeling. And we got these answers that are giving these very, very high stellar masses. And so, the question is like, what's wrong with this? Is it our cosmology? Is it our modeling of galaxies? Is it the data themselves? And then how do we move forward and actually understand really what's going on with this population? One potential explanation is that there's very, very early, very massive black holes, which would be unexpected, I think. But it's a possibility that some people have put into the modeling, which would be strange in different ways. But either way, these galaxies that we're starting to find are very different than ones that we've been finding before. And I think we're very excited to try and take follow-up spectroscopy of them to really pin down the physics that's happening in these things and understand why we're seeing this kind of very red light distribution from these distant galaxies. And then also we're starting to see another population of galaxies in the distant universe. This is actually a paper that Erica led. So we knew that our census of galaxies was incomplete. This has happened in the last 3 talks I've given. I don't know what it is about the scheduling, but yeah, thanks. So we knew our census of galaxies was incomplete. If you look in the submillimeter, you can say that half of all the star formation is obscured by dust. And we can't count up all those galaxies because they're too red. So we know we've been missing them, and they were too faint to see with Spitzer. And for the first time, we're finally starting to see this dust-obscured population. So this is a GIF. It'll go from HST to the JWST view, where you see all of a sudden this big red galaxy pop out of absolutely nowhere in the HST imaging. And so we found again, just in this very first data, we found a sample of about a dozen of these things that are red throughout, and they're kind of consistently elongated into these disks. So I think this is really exciting, as kind of like I was talking about before. Moving towards this kind of consistent picture of the galaxy population, both in the optical infrared and in the submillimeter. So we're finally starting to see these things and be able to spatially resolve them. And so with that, I want to kind of move from talking about the first galaxies to talking about galaxy size evolution. So this is the galaxy size-mass relation in the local universe. So this is a cartoonified version of a plot from Ariane van der Wel. These are star-forming galaxies and quiescent galaxies. And there's 3 kind of rules of thumb here. The first is that more massive galaxies tend to be larger. This is sloped upwards on both of these relations. At fixed mass, star-forming galaxies are larger than their quiescent counterparts. And then also these are these relations at redshift 0. If you go back in time, the picture remains relatively similar, but the normalizations both decrease, implying that galaxies were smaller at earlier times. And the big question that we have here is whether or not this picture was biased by HST's view of galaxies in the rest frame optical. So like I was showing you before with that picture of that face-on spiral, if you were trying to calculate the size in the rest frame UV, you get an answer that's basically what is the size of your small star-forming region, as opposed to actually being able to probe the stellar mass distribution of the galaxy. So to kind of put that a little bit into better words, light is a biased tracer of mass. And if you have radial variations in stellar population properties, you get radial mass-to-light ratio gradients. So the situation you want to be in is that your galaxy is the same color throughout, because then your mass profile and your light profile are the same. And so if you're looking at light in a fixed wavelength band and you're trying to measure the size, you're getting the right size. You're getting the same size as your mass distribution. On the other hand, you could imagine that you have an increasing mass to light ratio. So the outskirts of your galaxy are redder. And they could be redder either because they're older or they're dustier or they have more metals. And in this case, basically your mass profile is more extended out towards those red regions at the outskirts of your galaxy. And so when you're looking at a half light radius, it's actually underestimating the true size of your galaxy's mass distribution. Or the exact opposite case where the center is redder, and in this case your mass profile is compact towards that red center, and your half light radius is an overestimate of the galaxy size. And these aren't just kind of made up cartoons, despite the fact I'm showing cartoons here. You could imagine a galaxy with a central starburst that has a lot of young blue stars at the center. You would be in this case. Or a galaxy that has a bulge. Bulges tend to be old and red, and then you're at this case. And so hopefully that convinces you that correcting for these mass to light ratio gradients is actually essential if you want to understand how galaxy sizes are changing over time. And there's two ways that you can correct for this. The first is that you can use stellar population synthesis modeling to actually say, to divide your galaxy up into different spatial regions and say, what does the multi-wavelength distribution of light imply about the total stellar mass? So that is kind of, a model-dependent approach. The way that you want to do it is actually just directly look in the infrared, directly look at something that's tracing the mass distribution, which is what I'll get to later, but we couldn't do that for a long time because we didn't have access to rest frame infrared wavelengths in the distant universe. And so I'll talk about some of this stellar population synthesis modeling work. So I'll skip over most of the methods. Please feel free to ask me later if you're interested. But basically, I'll show you, once you correct for these mass to light ratio gradients, what is the effect on the observed size evolution of galaxies? So this is the evolution of the sizes of star-forming galaxies. So this is size at fixed mass, so basically just one point on this size-mass relation as a function of either look-back time or redshift. And so this is the growth of the half-light radii of star-forming galaxies. And interestingly, this size growth is basically tracing 1 over the Hubble constant. And what that tells you is basically that galaxy sizes are tracing the growth of the dark matter halos in which they live. This is kind of one of the fundamental parts of this galaxy halo connection, is that galaxy sizes and masses tend to reflect the sizes and masses of the dark matter halos that they live in. And interestingly, once we corrected for these mass to light ratio gradients, what we actually found is that that evolution is much, much flatter in the half mass radii of galaxies. And so this is saying that effectively from redshift 2 to redshift 1, the sizes of disk galaxies stay basically exactly the same, despite the fact that their halos are growing. So as Erica said, this was very surprising. It's kind of in tension with simulations. I think we're still working to understand why this happens, but I think kind of from a basic level, what this is pointing to is the importance of baryonic physics in driving the evolution of these sizes. And it's saying that perhaps the baryons are actually more important than the dark matter and what that's doing, at least in setting the sizes. We also looked at the quiescent galaxies. So again, this is size at fixed mass as a function of look-back time. And this is actually one of the most surprising results from early Hubble observations, is that the sizes of these red and dead galaxies grow dramatically over the last several billion years. And that's because it's hard to imagine why these things are growing when they're not forming any new stars. And so the kind of leading explanation for this is this idea of inside-out growth, which is that you can make galaxy sizes increase if you basically have them experience a lot of minor mergers, because minor mergers add mass just to the outskirts of the galaxies, so they kind of poof them up. But then you can go out and you can count how many mergers are there and how much does each merger actually contribute to the size growth of galaxies. And you find these curves. Where it works at low redshift, the number of mergers is enough to explain the size growth. But at high redshift, there's still a factor of 2, where these galaxies seem to be growing much more rapidly than could be explained by this inside-out growth model. And so the community kind of decided on this potential alternate explanation. Oh man, this is advancing too quickly. I gave away the punchline. There's basically this other explanation of perhaps the population is changing because you're adding galaxies that are joining this quiescent population at later times happen to be larger, so they're dragging up the median. But then when we went and measured these actual half-mass radii, we found this curve, which again grows much slower because these color gradients are evolving with redshift, and basically it perfectly matches these predictions from this minor merger model alone. And so it's indicating that the actual size growth of quiescent galaxies is just consistent with this minor merger growth model. So, like Erica said, these were both pretty surprising results. A couple people have confirmed them already with HST data. But, fundamentally, we're worried because this picture could still be biased, right? Because it relies, like I said, on this stellar population synthesis modeling, which is trying to get from the rest frame ultraviolet and optical distributions to the mass. And so it's implicitly assuming that there is no optically thick dust in the galaxy. And so what we wanted to do was actually this was the first thing I was really excited about with the JWST data, is to actually just go look in the rest frame infrared and see, are these things actually smaller than they looked like with Hubble? And so what we did is to look again at this first data of these high redshift galaxies and their sizes in now the rest frame infrared. So these are just some 3-color images of some example galaxies ordered from low stellar mass to high stellar mass. And then this is just the 4.4 micron data. This is absolutely beautiful. In Spitzer, these things probably wouldn't have been detected, or if they were, they would have been completely unresolved. And all of a sudden, we're seeing all this structure. It's amazing. And so we fit models to get the sizes of those galaxies in 4 microns. And then these are just the residuals from those 4 micron fits, just to kind of convince you that we're doing an okay job with the modeling. There's some interesting complex features like spiral arms that aren't included. But the really interesting thing comes from when you compare this 4 micron data to the model at 1.5 microns, which is the reddest light that we could have seen with Hubble. And when you do that comparison, you see that there's significant flux left in the centers of these galaxies. So all of this flux is flux at 4 microns that you weren't able to see at 1.5 microns because it was obscured by dust. And so this affects the sizes of these galaxies. So if you look at this in a different way, this is the size at 4 microns divided by the size at 1.5 microns as a function of stellar mass, just in 3 redshift bins. Where here the dashed line is basically the size in Hubble and the size in JWST is the same. And then above that is bluer centers, so the galaxies are larger than Hubble, and below is redder centers, and they're smaller than Hubble. And you can see that there's a significant effect here where massive galaxies are actually 30% smaller than they looked like with Hubble, which was basically exactly the assumption that we had gotten to from this spectral energy distribution modeling of the Hubble data alone. So this was really exciting. So it kind of shows that this picture of sizes, it is very different than this traditional picture. And because the strength of these differences in the size of galaxy in different bands, because this depends on stellar mass, and it might depend on redshift, it kind of challenges all of these accepted rules of thumb about galaxy size evolution that I started with in the very beginning. And so I think we're opening up a really interesting era of kind of mass-weighted structural studies of galaxies with JWST. And then also, this implies that most massive galaxies have red centers, even at high redshift. And so in a paper led by Tim Miller, who's a grad student at Yale, he's on the job market this year, he decided to kind of try and look for the first time whether or not these red centers were because galaxies are old or because they're dusty in the center. And we couldn't break this degeneracy before because the two effects produce similar distributions in the rest frame optical. And so he used this kind of color diagram. This is the U minus V color as a function of the V minus J color of the galaxy. And this diagram is handy basically because dust pushes things in this direction, and star formation, so kind of stellar ages, pushes things in this orthogonal direction. And what he found is that when he looks at kind of the change in color between the inside and the outside of the galaxy, most of the things he finds are in this quadrant of the plot, which is implying that the centers are redder because they're dustier. And so this is, again, it's really exciting. It's the first time we've been able to actually directly start looking at this. And it's kind of opening up this whole era of using this JWST data as a tool to understand how galaxies are growing. So not just how are their sizes changing, but what are their distributions of their stellar populations in this spatially resolved way. And so a project that I'm super excited about is called Pirate. And so it's basically to move to the next era of these studies. And so it's a Bayesian inference framework to actually map out the stellar population parameters in a galaxy. So what we're going to do is we're going to take all of that lovely imaging at all of these different wavelengths. And basically the work that I was telling you about before with HST, what I was doing is I was like smearing all of that beautiful data out to the worst resolution and then just kind of looking at annuli. But what we're actually going to do now is we're going to account for variations in the size of the point spread function across this really wide wavelength range and actually produce a model of underlying what is the stellar mass distribution of the galaxy, what's the star formation rate look like, what are the stellar ages, and actually get maps of how these galaxies are changing and growing. This is a big project. It's a very complicated task. Lots of wonderful people are working on this. I especially want to highlight Leah and Justice, who are grad students here, and then Elijah Matthews, who's a grad student at Penn State, who has basically provided us with a 10,000x speed up in some of the code, which is just incredible, with a neural net. So with that, I want to kind of move on to this last question of how and why galaxies stop forming stars. So, the Webb picture, like I said, we've only had data for a couple months, so this is mostly unexplored so far. I've started working with a grad student at Stanford, Richie, who's working with mock observations to kind of try and explore the best avenues for identifying and modeling these things. But this is kind of a stay tuned for once we've had more than 2 months to look at the data kind of question. So what I mostly want to talk about in these last couple minutes is a work that I've been doing at lower redshift. And the idea here is that if we want to understand why galaxies shut down their star formation, we want to look at galaxies that basically just underwent that transition so that whatever physics drove them to shut down their star formation, we can still see those signatures and they haven't been washed out by later evolution. And so what we did is we looked for a large number of these galaxies in the Sloan Digital Sky Survey at redshift 1/2 to 1. This is a stack of the spectra that we get. These things have a really distinctive spectral shape. They look like A-type stars. They have this really big Balmer break and this blue slope redwood of the break, which indicates they had a big burst of star formation. All the O and B stars died, so you're not seeing those anymore, but the A stars are still alive to dominate the light from these galaxies. And so we're doing a big multi-wavelength kind of study of this sample. It's called SQUIGGLE, which is a long convoluted acronym. Everybody needs a long convoluted acronym. This is a project that's done again in collaboration with a lot of really wonderful folks. And so these squiggle galaxies just quenched their major epoch of star formation. They just shut down this big burst. So to kind of quantify that statement, we had to do a lot of detailed modeling of their star formation histories. This turns out to be logistically very complicated. We ended up writing a whole paper on how to do this accurately, so ask me later if you're interested. But what we found is we could end up getting the fraction of the mass of these things that was formed in a recent burst, and then how long it's been since they quenched. And what we found is kind of a range of both of these properties, but most of these things formed at least a quarter of their stellar mass in a recent starburst that shut down within the last 200 million years or so. And so with this sample, we're looking at a lot of different things, but the one that I want to tell you about today is their molecular gas properties. So this is the Kennecott-Schmidt relation, effectively. This is star formation as a function of molecular gas mass. And the idea with this diagram is that stars are formed out of cold molecular gas, basically. So this axis is telling you about how much fuel you have available for star formation. And this axis is telling you how many stars you're actively forming. So of course, these quantities are related, because if you have more fuel, you're also forming more stars. So the idea of this experiment with these squiggle galaxies is that stars are forming out of cold gas. So did these galaxies shut down their star formation because they just ran out of the gas reservoirs to do so? And so we started looking at some of these post-starburst galaxies, observing them with ALMA to study their molecular gas reservoirs. And we found that both of the first two galaxies we looked at were significantly detected in molecular gas, and they lie pretty far off this relation, especially this one. So these things have tons of fuel, they're just not forming any stars out of it, which is very surprising, and we were trying to figure out for a long time what was going on, and we thought maybe we just looked at two super weird galaxies. So we got a larger sample, and we detected, again, 4 more of these, significantly offset from this relation. In particular, these two galaxies have gas fractions of 20%, which is an order of magnitude higher than you would expect for galaxies that aren't forming stars. And then we found a lot of non-detections, which in itself is also strange because we selected this population to be pretty uniform. So what's going on with their molecular gas that we're seeing such a diversity? And so it turns out that galaxies with more gas quenched recently. So this is why, ultimately, why I spent so much time working on these time-since quenching values, is that it turns out they're very important. Because all the galaxies we detected in molecular gas quenched within the last 100 million years or so, and then everything that quenched longer ago doesn't have any gas left. And so that implies that this gas in these galaxies, 10 to the 10 or more solar masses of gas, disappears in just 85 megayears, which is like an insanely fast timescale because if this was due to star formation, it would be more than a gigayear. We also found kind of the weirdest galaxy that I've seen. So this is a galaxy, this is an integrated line map from ALMA showing this gas that's extended on a 60 kiloparsec scale outside of this galaxy. So that's like way out into the circumgalactic medium. And so this is the velocity structure. It's got this kind of biconical structure here. And we were trying to figure out, like, is this an outflow? What on earth is going on with this thing? And then Justin Spilker, who led this paper, went and got an HST image of it, where you see, it's a little faint, but this is the starlight from HST. So this thing is a merger remnant, and that's actually gas that's in the tidal tails. So basically this thing experienced a gas-rich merger, and during the merger, basically that merger dragged more than half of the gas in the galaxy and just chucked it way out of the galaxy, which is actually really surprising, and we've never seen this before. This is the first galaxy outside the local universe that has molecular gas detected in tidal tails. If you try and put it on a diagram, basically it lies out in the middle of nowhere in terms of the mass of gas in the tail, the fraction of the mass that's in the tail, and also the total extent of that tidal tail. So we're kind of selling this as this kind of new quenching mechanism where, again, you can stop star formation in a galaxy by just grabbing the gas and chucking it out into the middle of nowhere where it can't form stars anymore. So this is the kind of NRAO press art for this thing. We're not sure what's going to happen to it next. Maybe that gas will fall back on and start forming stars again. And then we're doing a lot of work to kind of follow up on this, to pin down the timing of this disappearance. This is work that's led by David Seton, who's a grad student, also again on the job market. And then working to look at the role of AGN and mergers. We're also looking at higher redshift. This is work that I'm doing with Eliza Beveridge, who's a grad student at Berkeley. And then, hopefully our best kind of explanation of how you get rid of this gas on such a short time scale is that maybe it's heated. So hopefully we'll be able to look at the warm gas reservoirs directly with JWST in near spec. But that's a cycle 2 thing, so stay tuned. And then I want to kind of conclude with a couple of the main science takeaways and then a couple of things that I'm really excited about for the future. So we found that massive galaxies seem to form much earlier than we were expecting. I also showed that galaxies are much smaller than they looked with Hubble, and showed you, hopefully, that these sizes can be used as a tool to understand how galaxies are assembling their stellar masses. We're also already starting to see this kind of previously invisible universe, these galaxies that we couldn't see before at optical wavelengths. And then lastly, I showed that gas reservoirs and quenching are linked, but not necessarily in the way that we thought. So just a couple things that are next. Erica mentioned, so I ran for a long time this program called Respect as Part of Research, which are peer-led workshops that are intended to prevent harassment and discrimination in STEM This is a completely unhelpful, this is a whole poster, mostly just to advertise. If you want to talk to me about this more, I think I have more meeting slots, so especially the grad students. We ran this for a long time as a grad student-led program, and we've got it in kind of a nice portable package where we have these workshops that you can run. And then as far as other things or what's next, science-wise, I'm excited about this JADES program, which is 800 hours of time with JWST, both on NIRCam and NIRSpec. The medium data is as deep as the deepest Hubble data that has ever been taken. And then there's another deep layer that's, again, significant integration on top of that. So the way that I know Erica, we're co-leading this seismorphology working group, and then I'm also co-leading this quiescent working group with Christina Williams. These are just a couple of JADES images. They don't look as beautiful on this projector, so trust me, these are amazing. This is the stack of galaxies that's mostly unresolved in HST. We're going to be able to study the structures of these things in detail. This is this beautiful flocculent spiral at a redshift of like 1.5. And then also, this is another star-forming disk where actually what we're seeing here, these little red regions, is all PAH emission, which is going to be really exciting to study. I'm on a couple of other programs. I'm really excited to look at a spatially resolved view of the distant universe with this Pirate project I talked about. And the reason that this is so exciting to me is that we're finally going to move beyond this era where we've been basically taking an entire galaxy and reducing it to a single data point and then putting it on a scaling relation. And we're actually going to be able to map what are the physical mechanisms that are causing galaxies to grow and change, and how are galaxies moving through these different kind of scaling relations. I'm also really excited about this idea of the previously invisible universe, and finally starting to get a census of how much star formation is happening across cosmic time, and what stellar populations basically we haven't been able to see so far, and how they contribute to galaxy evolution. And then also, lastly, I'm really excited in the coming years of JWST about building up a complete picture of the multi-phase ISM in distant galaxies. So far with Hubble, we've been able to look at rest frame visible and near IR, basically tracing starlight. And then with ALMA, we've been able to look at cold gas and dust. And now for the first time with Webb, we can basically get a picture of the warm gas and the PA emission, which is a type of dust, in the middle part of the spectrum. So this is the first time that we're going to basically be able to build up an actually complete picture of the stars and the gas and the dust in the same set of galaxies in the distant universe. And so that's going to be actually the first time that we're going to be able to directly probe the physics that's governing star formation, dust formation, and destruction in these distant galaxies. And then also a lot of work we can do on the modeling side to actually understand what are the light coming from these distant galaxies and how do we effectively model that. And then lastly, I'm really excited about what we haven't figured out how to ask the questions about yet. I showed you just a bunch of results from these first couple months of JWST data. But again, I hope that we continue looking for things that we hadn't expected. And I think, if I was giving this talk in a year from now, I think the things I would talk about would be completely different because we just haven't found all of the crazy things in this data yet because it's just too early. So with that, I'll leave these conclusions up and take any questions that people have.
Thank you for an amazing talk, Wren. Yes, questions. Let's start with the graduate students. Got one up here.
First of all, great talk.
Thank you.
I love seeing all of the new JWST data. Absolutely gets my mind buzzing every time. I wanted to ask you about, so when you were talking about these recently quenched galaxies, I'm trying to remember, there was something back when I did a little bit of citizen science with Galaxy Zoo.
Yep.
There's something in that data called vorwerps, which are, if I recall correctly, basically just a recently shut off AGN that's lighting up the gas that's been blown out.
Yeah.
Are those something that you're looking at potentially with regards to figuring out this sort of quenching and all that stuff? How does it relate to what you already discussed?
Yeah, no, that's an excellent question. Thank you. So this is a little bit of a different population than those guys. I think in general, it's very clear that AGN and quenching are linked. The question of how is the complicated part, because AGN vary on such short timescales that it's really hard to do that work. A lot of people here are doing very heroic efforts at kind of disentangling the physics that's going on. So we do know that AGN are important in quenching this post-starburst population. My colleague Jenny Green wrote a paper about elevated AGN fractions in these post-starburst things. But really what we're looking at here, that was kind of a selection based on the morphologies of the galaxies and looking at those outflows. And here we're doing a selection that's based on their spectra. So what is the starlight and how are we seeing, the shutoff in star formation from that? But I think they're kind of complementary samples, and I think there's, to some extent, there's a big zoo of different recently quenched galaxies, and the hard part is really trying to get all of those together into a coherent narrative of all of the different ways in which galaxies stop forming stars. And these are kind of just the easiest ones to identify, which is why we focused on them.
Hi, I was wondering if you could comment on how the largest galaxies that you've found, what do they say, for instance, the constraints on reionization, like the timing and the clumpiness of it?
Yeah, great question. Yeah, so the galaxies that I talked about are kind of after reionization has already done most of the work. They're at kind of redshift, 6 to 10. So people normally, when they're starting to actually think about what are the galaxies that are reionizing the universe, they're looking at kind of higher redshifts. So the paper that I was on about this was Rohan Naidu's paper, where he identified a couple of candidates that seem to have survived the photometric redshift 0-point updates, if you've been tapped into that at all. They appear to be mostly real, we think. And so those things are extremely bright and extremely massive. I don't have the plot up. And weirdly, they're disks already at one of them is a disk apparently at redshift 11, which is just absolutely bonkers. We didn't think disks could survive that long. So I think it's a little bit early. I think there was a paper today on UV luminosity functions from Webb, but I didn't read it because I was meeting with people instead. So, I think we're starting to do work on that. And I think, the patchiness in particular is something that I think folks are really interested in, that we should get a constraint on now, and then also with the Cosmos Webb program, which is a Cycle 1 program that looks at a really large sky coverage. So that's kind of hoping to account for cosmic variance. Yeah.
Hello. So I also want to ask about the supermassive early. So one question I have is, if you did, what methods you used for the mass? Did you do any velocity dispersion comparison to see if you got the same thing? And what if these galaxies are actually that massive and the dark matter halos are that massive? What does the universe look like? What are the consequences for the Big Bang model?
Yeah. No, great question. So basically the modeling that we did in this paper so far is based on photometry, because spectra are hard and this telescope's only been there for 3 months. So, we'll get to it, hopefully. The SEERS program is hopefully targeting these in a month with spectroscopy. So we can't look at velocity dispersion. So it's basically just we're looking at the spectral energy distributions of these things and we're trying to model those. And one of them we have an absolutely amazing constraint on because it happens to lie at the perfect redshift where we get 0.3 in the 410 medium band filter. So you know exactly what redshift it is and you know exactly how strong that line is. That's not the most massive one, it's one of them. So the question of, if these masses are exactly, too high, it's very spooky to me that in the kind of post-referee version of Mike's paper on the what this implies about cosmology, it's right on the limit of what is allowed at all by cosmology. That's very scary. I really don't think we're at a point yet where we can say that our cosmological model is wrong, because galaxies are really hard to model. Like, there's a lot of physical processes going on. So I think it's likely that there's some contribution from line emission or potentially black holes. But I think, again, you know, these galaxies are we thought that they wouldn't be there at all, or they would be extremely rare, and we found like 6 of them in the first 40 square arc minutes. And so I think the question you asked, I know I'm kind of, you know, dodging the question, and I think it's just because we haven't had enough time. But I think it's kind of the question that's on everybody's mind right now. Yeah.
Hi, thanks for a great talk. You mentioned that some of these results are in tension with simulations, and I was just wondering if you could say a little bit more about that, and do you think it's a problem of like observational bias or assumptions made in the simulations?
Yeah, totally. Yeah, so I think the place that I said that about was about the evolution of the sizes of star-forming disks. And, you know, I think it's a hard problem, right? Because basically, you know, the observations are constrained to match the redshift 0 universe. And then it's a question of how do disk sizes evolve between now and then. And so those are kind of the predictions from simulations, are expecting these sizes to evolve as the dark matter halos evolve. And we're finding that the sizes are growing much, much more slowly. And I think what that's saying is there's kind of 2 possibilities. One is you can slow the size growth of disks if the spin of your dark matter halo also evolves over time. So perhaps there's evolving halo spin parameters that are stronger than we thought. Or perhaps, you know, you're not including all of the relevant physics in your simulation. And in particular, I think feedback from AGN is still something that's extremely difficult to model. There's a lot of things that are just tricky to model. And so I think the question of like, how do we fix this? How do we get the simulations more to agree with these observational results is an interesting one.
So you mentioned in your last figure there, great talk by the way, again,
Thanks.
I really loved it, that you have these galaxies that are recently quenched and they have a ton of molecular gas and then it goes away.
Yep.
So what's your favorite pet theory on what's going on there?
Yeah, totally. I skipped this a little bit because of time, so thank you. So my theory is that the gas is being heated. So what we're probing there, this MH2, is based on CO measurements. And so what I think is happening probably, because the only thing I can come up with that could happen on an 85-year mega-year timescale is that you're heating the gas. And so you're not seeing it in CO anymore, and you would see it in the warm gas instead. But if you have another idea of what could get rid of this much gas this quickly, I would love to hear it.
Okay, I think, sorry, Amy, I'm sorry. Yeah, you got plenty of time. Thank you, everyone, for coming. Thank you, Wren, for an excellent talk. Thank you, everyone, for great questions. Thanks again.
Thanks.